Thank you, Dr. Xian, and hello everyone. Thanks for coming. My name is Beiming, and the topic of my thesis is depth completion of glass surfaces from a single view polarization image. So the motivation of this thesis is that detecting and mapping of glass surfaces has been a difficult problem for both computer vision and robotics community. The major reason is that the major depth sensors cannot measure depth for glass or transparent objects in general. For example, the stereo camera, they will return the depth of objects behind the glass surfaces, while active sensors like LiDAR and time of flight camera does not provide depth measurement for the entire glass surfaces because of the specular reflection on the glass surface. Now, not being able to detect a glass will cause a lot of problem in robotics. For example, if you fly a drone in this room, and if there is no curtain on this glass windows, it is very easy that the drone will bump into those transparent objects. It might be okay for some of the drone robots, but it is definitely a disaster for aerial robots or other kind of robots. So in this thesis, we look at another kind of sensing modality called polarization camera. So before getting to the pipeline or the proposed methods of this thesis, we'll first take a brief look at the principle of light polarization. So light waves are essentially electromagnetic waves. They oscillate perpendicular to the direction of propagation. And polarization refers to the orientation or some other characteristics of those oscillations. Our sunlight and most of the indoor lights emit unpolarized lights, which means the light intensity oscillating in different directions are roughly the same. So after the unpolarized light hit a linear polarizer, as visualized in the bottom figure here, only part of the light will be able to pass through. So, and the light after passing through this linear polarizer will only oscillate in one direction, which means the light is linearly polarized. You can view this as a combination of two coherent waves along two orthogonal directions. There's also circularly polarized light, which is essentially the combination of two phase-shifted waves, which we will not cover this thesis. Now we introduce a few notations or variables that are important for us to understand polarization. So as mentioned before, after passing through a linear polarizer, the light will be polarized. And we write down the polarized intensity as I phi pole, and phi pole here represents the angle of the polarizer. If we have access to 4 different polarized intensities at 4 different angles, I0, I45, I90, and I135, we can write down the Stokes parameters, which is one of the common variables used by people to represent the polarization state. So the first entry of the Stokes vector S0 represents the total light intensity. You can calculate that simply by adding up the light intensity at 2 orthogonal angles, and S1 and S2 represents the difference between the intensities at 2 orthogonal angles. Now, with the Stokes parameters, we can further derive 2 important variables. The first one is called degree of linear polarization. Now, if the light is unpolarized, this degree of linear polarization rho will be 0. And if the light is fully polarized, which means the light is only oscillating in one direction, this variable will be 1. And the second important variable is called angle of linear polarization. It essentially represents the dominant direction of light oscillation. So with the brief introduction to light polarization, we can now take a look at the polarization camera. So our polarization camera is manufactured by Sony. It is called Phoenix IMX264, and it comes with 5 megapixels. So different from regular cameras, those polarization camera has an extra layer of polarizer on top of the pixel layer, which means that now the light intensity collected by the pixel array is now polarized light intensity in one of the 4 directions, either 0 or 45 or 90 or 135. Now, as we've already seen on the previous slide, we can calculate the Stokes parameter and angle and degree of linear polarization from those 4 polarized intensities. Now, Therefore, every block of 4 pixels will make up a calculation unit, which gives us 1,000 times 1,200 pixels of polarization information. And our specific model comes with a Bayer filter overlay, which means that every block of 16 pixels will make up a mega calculation unit, which gives us RGB information. As a summary, this polarization camera gives us polarizing intensity at 4 different angles. And from that, we can derive RGB images and angle and degree of linear polarization. So now we can take a look just at an overview of the entire pipeline proposed by this work. Great. So there are a few major components in this pipeline. So the first one is class segmentation. We're trying to get a segmentation mask which classified between the glass and the non-glass regions. And with that segmentation mask, we can clear out the incorrect depth measurement from stereo camera or incorrect depth estimation from a monocular depth estimation network like depth anything. And from that, we can get the modified depth, where there's only depth for the solid frames around the glass regions and no depth for the glass surfaces. And the second and another important component of this pipeline is the glass surface normal estimation network. So given a polarization image, we're trying to estimate the surface normal for the glass region. And we'll combine the estimated normal for the glass and the surface normal derived from the modified depth, and we can get the combined surface normal image. Finally, we'll use the combined surface normal and the modified depth and shape a global optimization problem, which gives us the final output depth. So it is helpful to get this big picture in mind, and I'll get into every single modules afterwards. So the first module we'll take a look at is the glass segmentation model. There have already been a lot of efforts in the literature where people are trying to classify between glass and non-glass regions. A lot of the previous efforts use RGB plus depth information to do that, and they rely on contextual information. For example, if there is a boundaries of glass surfaces or there exists a reflection, then people say that, well, this is highly likely to be a glass. However, this method is not reliable enough when it comes to like open windows or open doors. So recent years, people have tried to use RGB plus polarization information to do the same thing. The motivation behind that is because the light coming from a glass windows or transparent objects usually has a distinct polarization property, meaning their angle and degree of linear polarization will be unique. So this thesis also utilizes the same property or the same motivation. We'll also try to use RGB plus polarization information for this task. In this work, we will borrow a dataset called polarization glass segmentation dataset from a previous work that provides us with a lot of polarization images of glass surfaces in real life, and it also comes with hand-labeled segmentation masks. One of the examples is shown on the bottom of the slide. So with the dataset, we now adapt a multimodal sensor fusion neural network called CMNext. It is a transformer-based network. Basically, it takes in RGB information, RGB images, and any other kind of sensor inputs, for example, depth or event cameras. But in our case, the extra input is angle and degree of linear polarization. And the network will fuse the information coming from the RGB channel and the extra sensing modality channels together in the middle of the network using cross-attention mechanisms. But we'll skip the details here because it is not the major contribution of ours. So we train this CMNext on the PGS dataset we mentioned before using standard cross-entropy laws with a few tweak in learning techniques. And the final trained model actually outperforms existing methods on the validation dataset. The major reason is because this network is powerful. And I shared a few validation metrics on the bottom right here. You can see that the CMNext trained on RGB plus polarization information outperforms the PGS net, which is actually the network proposed by the original author, which shows the superiority of the the network. You can also see that the CMNX trained on RGB plus polarization information also outperforms the one trained only on RGB informations, which actually indicates that polarization informations are valuable and valid clues for us to segment the glass materials. And further, we test the trained model on the actual data collected by our polarization camera. And since we don't have the ground truth segmentation mask, we don't label that. We instead visually inspect the correctness of the segmentation results. So I took a few images of a conference room with a glass door and the glass walls, and there's also another glass window behind me. So you can see the reflection of those windows on this glass surfaces. So as shown in the top row, there are two examples where the network gives us great separation results, segmentation results, and that happens for most of the cases. However, there are a few failure cases where the network fails to give us perfect or correct segmentation mask. For example, the one pair of segmentation results shown in the bottom, the network is confused by the light intensity from the window behind me. Therefore, it fails to segment these pixels out as glass regions. But we believe that this network is good enough for our usage. And we'll proceed to the second module. Is there any questions for the glass segmentation part? Yeah.
You train on that, is that dataset part of your validation dataset?
No, so the PGS dataset comes with a training part and a validation part. So I train on the training part, a training dataset. This validation results come from the validation dataset of the PGS dataset. And this is the testing data I collected myself.
So you directly use them for the training?
Yes. Yeah.
Oh, that's great.
But the sensor, but they use similar sensor as ours. Yeah. So that's kind of a little bit of generalization, but not too much.
Nice.
So how would it perform if you only looked at the two polarization channels, the two properties? Right. So right now you have RGB, right, as well as the angle and then the degree of linear polarization.
Yeah.
Right. But what happens if you didn't have RGB?
Great question. I should have done that, but I don't have the results. But I would say that it will be worse than RGB only information, but not too much. It's likely around 50 or 70 IOU, but because it's still, because as you can see from these examples, it's not a very great example, but you can sort of see that. Can you see that on Zoom? But you can see that the glass surface has a uniform angle of linear polarization, and the degree of linear polarization for the reflection part is different from other parts. But yeah, I'll get a little bit more into details of why angle and degree of linear polarization is unique for glass surfaces. But they're similar to RGB images. So yeah, hope that answered the questions. Okay. All right. So we'll proceed to the second module, which is the surface normal estimation model. So there have been also a lot of research in this line of work, and people have tried to use RGB or RGB plus polarization information to estimate the surface normal based on inputs. And they usually do that in a supervised learning way, and they relies on the ground truth surface normal of the data. However, those kind of learning-based methods doesn't work directly on the glass regions because it is inherently very hard to get a ground truth surface normal for the glass regions, because you cannot get the depth for that. Therefore, you cannot get the surface normal for the glass regions. There are also physics-based methods. It utilized the polarization principle. So it utilized the light reflection and it solved the surface normal based on a degree of linear polarization and refractive index of the object materials. But They doesn't work on the non-transparent objects because they assume that there's only reflection intensity and there is no transmission intensity. Therefore, we need another way to solve the glass surface normal estimation. This is when I will get a little bit more deep into details about why light interacts with the glass surfaces uniquely. So I use two symbols here, perpendicular and parallel, to represent the oscillating directions of the light portion we're looking at. So perpendicular means the light is oscillating perpendicular to the plane of incidence, and parallel means the light is oscillating parallel to the plane of incidence. And when the light hits a glass surface, part of the light will be reflected, and another part of the light will be refracted twice and actually we got it transmitted. So I write down R perpendicular and R parallel to represent the portion of the lights get reflected. And that depends on the angle of incidence and also on the refractive index of the materials. We can also write down T perpendicular and T parallel, which represents the portion of lights get transmitted. And there's also another variables called denoted as phi perpendicular. So for the plane of incidence, we have the normal vector, which we can calculate. And we project the normal vector into the image coordinate. And phi perpendicular is the angle of that projected normal. And since we're now looking at the polarization camera, we assume that the light intensity after reflected and transmitted by a glass surface passed through a polarizer array and received by our camera. So we write down the polarization intensity as I pol, and we can calculate this the polarizing intensity with the following equations. This is purely physics-based equations, and the takeaway from this is that with access to IR represents the light intensity before reflected, and IT is the light intensity before transmitted, plus angle of incidence, refractive index of materials, and phi perpendicular, we can calculate the theoretical polarization intensity we would receive on a polarization camera if it's looking at a glass surface. So as mentioned before, the difficulty with glass surface normal estimation for glass regions is because we don't have the ground truth surface normal, and we cannot use supervised learning techniques on that. But instead, now with this equation, we can sort of generate a synthesized data set with a ground truth surface normal. And the data synthesis pipeline looks like follows. So we first randomly pick a pair of image as IR and IT, and we assume that the entire image is a flat glass surface with a uniform surface normal, with a uniform but randomly sampled surface normal. And because we're using a simple pinhole camera model, we can calculate the viewing direction of every single pixel in the image. And with that, we can calculate the pixel-wise phi perpendicular and theta, which is the angle of incidence. And we plug into the equation we've seen in the previous slide, and we can get the theoretical polarized intensity at 4 different angles for each pixel. So anyways, the summary for this part is that we synthesize the data set, and the data set would composed of a synthesized polarization images plus the corresponding ground truth surface normal. Now, there is a lot of simplification here and there, but we use this simple pipeline here as as a proof of concept that it could work. So after getting this data set, we can finally use a standard supervised learning techniques to estimate the surface normal for the glass surfaces. So we use a small, concise convolutional neural network composed of 7 convolutional layers and 2 fully connected layers, nothing special. And the input to the network is polarization images, and the output is 2 angles, the yaw angle alpha and the pitch angle beta. And from that, we can derive the surface normal vector. And since the supervised learning would define the loss based on the angle between the estimated surface normal and the ground truth surface normal. So ideally, our estimated surface normal should be of the same direction as the ground truth surface normal. So we train this network on our fake or synthesized data set. And of course, we get good results on our data set. And the question is how that performs on the actual data. Because the actual data would can be very different from the data we have in the synthesized data set. So again, since we don't have ground truth surface normal, we instead visually inspect the correctness of the network. So given an input image, which is a polarization images, we reconstruct the RGB image from that, and we feed that into depth anything, which is a monocular depth estimation model, which gives us metric depth. And from that, we calculate from this metric depth, we can derive the pixel-wise surface normal by calculating the gradients between neighboring pixels. And the color in the surface normal picture represents the direction of the surface normal. And using this glass segmentation mask we get from the first module, we can clear out the surface normal corresponding to the object behind the glass regions. And we get this rectified surface normal. And we fill in those empty pixels with the estimated glass surface normal from our network. And we finally get this combined surface normal. And as you can see from this image, that the color of the glass regions actually looks similar to the color of the frames around the glass regions, which indicates that the surface normal estimated by our network is similar to the surface normal of the surrounding frames, which indicates that network is sort of doing the right job. And here we give more results just to show that our network gives us correct results. So we have a camera moving from the left-hand side from the right-hand side of the conference room gradually to the left-hand side of the conference. And as you can see in every single surface normal images, you can see that the surface normal of the glass region is roughly the same as the surface normal of the surrounding frames. And from the left-hand side to the right-hand side, you can see that the color of the glass region is changing from lighter green to a darker green, which indicates that the estimated surface normal agree with the motion of our camera. So if we take a look at the pipeline again, we can see that we now has the glass segmentation part. From that, we can get the modified depth. And we also have a combined surface normal. And the only module left is the global optimization part, which gives us the actual output depth. Now this part, so shaping the depth completion problem as a global optimization problem actually come from one of the previous work where the author defined this global optimization objective. And the global optimizer for this problem is the final output depth we use. So this objective composed of three terms, and the depth term, the first term, depth term, is used to keep the estimated depth of non-glass pixels the same as their observed depth, because monocular depth estimation and stereo camera will gives us valid depth measurements for the solid objects. And the normal term is used to ensure that the surface normal derived from estimated depth would be the same as provided surface normal, which is our combined surface normal. And finally, the smoothest term is used to keep the depth of neighboring pixels roughly the same as each other. And finally, we'll solve this with sparse Kulicki factorization, same methods used by the original author. Here are some of the depth completion results. As you can see from the depth anything output, you can see those objects behind the glass regions. However, in our output depth, we no longer see those objects, and we can see that the depth of the glass region is correctly estimated, or partially correct estimated. But there are also cases where the segmentation mask is not perfect. Therefore, we can get those funky looking output depth. That is because the normal term and the smoothest term in our global optimization object is trying to smooth out the depth in a certain region. Therefore, you can see those those circles with darker colors. But I will show, so this is, I took a few hundreds of pictures of the same room, and the left-hand side is the depth estimation for every single frames. And you can see that for most of the time, we'll see a valid depth estimation results. So a few future works. So right now, one of the major things is that right now this whole pipeline takes around 45 seconds on desktop CPU. the main reason is because the global optimization part is very hard to solve. Therefore, a lot more efforts is required before we can actually put that onto a mobile robot. Finally, I would like to thank my advisor Vijay and also Pratik, who have been kind enough to give me a lot of suggestions and support. I would also like to thank my lab mate Vijay, Fernando, Anthony, and Alex, and also Manazi from UTH for their support and help. Thank you. Leave the slides on while there is any questions.
Any other questions?
So, please go ahead. So what's the inference time of the whole pipeline?
The whole pipeline is, so there are actually two parts, right? So the first part is like two neural network inference on GPU. And with a desktop GPU, you can do that, I would say like 2 hertz per second, because right now I use a pretty large network for the segmentation part. Yeah. Also, that anything is a huge network. So that takes a lot of time. You can simplify that by maybe using like a single network as a feature extractor, and you have different paths for segmentation paths, for depth estimation paths, and surface normal estimations. That will save a lot of inference time. And the global optimization problem is solved on CPU. Although we use like sparse density factorization, which makes this a lot faster than it should be. Well, it makes it a lot faster. It still takes 45 seconds on the desktop CPU, which is bad. So yeah.
Maybe I missed some details while you were explaining it. So if you can just explain when you were generating the depth you were using the synthetic data to actually generate the surface normal. Sorry, not the depth.
Yeah.
So why were you taking pairs of images?
Oh yeah. So if you're looking at the glass surface, part of the light will coming from outside. And part of the light will be the reflection of the indoor lights. So that's why I take randomly take 2 images.
Also, they have to be random. They don't really have to be correlated.
Yeah, they're not correlated.
Okay.
Which makes it more different from the actual.
Yeah. Thank you.
So I think the major reason this could work is because we generate the polarized intensity at 4 different angles, and the relationship between those 4 polarized intensity is the actual clue we'll use to say that, well, there might be a glass, because the glass materials would make those for polarized intensity related in a different ways from other materials. So
Derek, you want to get ready?
All right.
Any other questions? Let me just make sure. I don't think we can. Thank Beiming again